Okay, good morning. Welcome to the Exascale Computational Engineering workshop. My name is Gianluca Laccarino. I am the director of the Thermal and Fluid Science Affiliates Program, which is co-sponsoring or co-organizing this event together with the HPC Advisory Council. We have this workshop as sort of in between the HPC conference that was held here Monday and Tuesday, and then the TFSA conference that will start this afternoon. So this is sort of a bridge between these two events this week. As you can imagine, we've been very busy, and it's a pleasure. It's a pleasure to welcome you here to the conference. I'm pleased to give the first presentation of this workshop, and then introduce our distinguished speakers that we have for the morning. Before going ahead with the presentation, I wanted to spend a minute telling you about the TFSA program, the Thermal and Fluid Science Industrial Affiliates Program. Is a program within the Mechanical Engineering Department here at Stanford, and has a long history, and is our way to really establish and continuing interaction with industry. We have been very effective in creating a network across the world. These are our current industrial affiliates. You see participants or corporations from everywhere in the world, and also very diverse in terms of their technical focus. So aerospace, automotive. So in spite of the fact that this is a program started and squarely within the Mechanical Engineering Department, we have a very, very broad reach. What else? The conference is starting this afternoon, as I said. It's a packed event. We have 2 days of that include a lot of presentation, mostly given by our students. So these are really intended to give you a fresh look at what's happening in terms of research in the thermal and fluid sciences at Stanford. We also have some special invited talks, and we have about 45 guests from our industrial affiliates, and then others from government representatives. So this is the audience and some of the people that have joined us this year. In addition to the presentation of the research program, in 2011 we started a sequence of workshops. Every year we have a different topic. These workshops are an opportunity for our industrial affiliates, for the representatives, to actually give us some hints, some insights, some ideas of what is that they are working on, what is that they are concerned about in terms of fluid and sciences, thermal and fluid sciences in their own organization. And this year we decided to focus on exascale computing, or perhaps a more appropriate way to say it would be next generation computing. What are our goals and insights into what's happening? And we have, as I mentioned, a very nice list of speakers. They actually have a strong representation from our affiliates, but also representation from government labs, from various institutions here in the US. So I'm very, as I said, very excited about the program. I'll be the first speaker, but really just give you a little bit of an introduction to a new program called PSAP2, which is sort of the reason why we decided to organize the workshop on this topic. The PSAP2 program has not actually started. It will start officially, hopefully March 1st. And one of the key ingredients is exascale computing. So in some sense, I'm in a lucky position to give you a presentation on things that we have not really done. So it's sort of more of preview of things to come, rather than actual hard results or conclusions. And so let me start right away then telling you about this program, and I want to, as I mentioned, give you really more of a broad overview of where we are, what have been how we got here, actually, more than everything else. The Department of Energy, in particular NNSA, in 1995 started this ASC program with the objective of supporting the shift from test-based confidence to computational-based confidence. So how we can use computational tools to really establish and decision-making processes that would provide confidence in critical decisions we have to make. Stanford has been involved in this program as one of the university's partners since the very beginning, and actually it is the only university that's been continuously funded under this program since 1997. This is a fairly large, sizable program, so this has been a fantastic opportunity for us to really foster our agenda in computational science. The first part of the program, the first 10 years, were really focused on multiphysics integration. Our overarching goal was the simulation of a full end-to-end jet engine, and the objective was really to understand if these computations are actually even possible at the scale of a largest supercomputer in the world for a realistic application like that. The second part, after 2007, was the PSAP Center. PSAP stands for Predictive Science Academic Alliance Program, and predictive is the keyword here. The addition is that we are continuing to do multiphysics integration, but in this case, we are adding the concept of confidence. How can we quantify the confidence in those simulations? Uncertainty quantification is sort of the keyword for that. Our focus is still a propulsion system, in this case, an high-speed propulsion system, an hypersonic vehicle combustor, a scramjet. And the program just finished, or this project just finished in April, early this year, in 2013. But as I mentioned, we were successful in actually obtain a continued or a new project. PSAP-2 was awarded in June 2013. Still not active, as I mentioned. Hopefully by March will be officially started. And there is, again, one additional component, still the two previous components that I mentioned, but now the new ingredient is really exascale computing. So what is the project about? Well, first of all, it's Stanford in collaboration with 5 other universities in the country, although much of the weight is on Stanford directly, and in collaboration between mechanical engineering, aero-astro department, computer science, mathematics, and all part of the Stanford effort. So the focus is really to perform and continue to demonstrate predictive multiphysics simulation. In this case, the application is not a propulsion system, it's a solar receiver. I'll tell you a little bit about that in a second. But as I mentioned, the key is also the next generation compute system. So let me start from the solar receiver. I don't want to give you too much of details, but just to bring you up to speed with that, these are so-called solar thermal system in which a vast array of mirrors, an heliostat in this case, concentrate the solar radiation onto a point on this tower. A view from the front, this is sort of the target of that mirror concentrated light. And if I take a cross-section of that tower, there is a fluid flowing through it, which is, depending on its optical characteristics, transparency characteristics, either is transparent to the solar radiation and so gets heated by conduction of this solar radiation to the walls of this cavity, or actually is an opaque, like a curtain of particles, and gets heated directly from direct absorption of the light. Now, in our system, we are doing something different, where we have a turbulent flow laden with particles. The interaction of these two create a non-uniform concentration of particles, and radiation then is absorbed locally where there are clusters of these particles. And so the idea is to go from surface-based heating and transfer of the radiation to a volumetric heating. That's sort of the key principle. So our scientific challenge is really to model this coupling, turbulence, radiation, and particle transport. It's a very complex coupling, and it's not very well understood. It's still, for example, if this is a self-sustained cycle, turbulence and modulated by particle and particle absorbing radiation will create thermal plumes that then regenerate turbulence. And this cycle is not necessarily was not very clearly understood so far. This is an early calculation that we did, where we start with an homogeneous distribution of particles in a turbulent box. You see that very quickly, subject to radiation, very quickly we generate very high concentration. The blue things here are very high concentration of particles. Corresponding to that, there are thermal plumes, these high regions of high temperature, that then sort of continue to regenerate turbulence and self-sustain the process. This is the first demonstration of this process that was done early this year, and it's actually interesting that changing the property of the particle changes this picture completely, and sometimes you don't have the turbulence decays. So it's an interesting scientific challenge. It's very complicated calculations. They are not just related to thermal devices, solar thermal devices, they have very broad industrial application, including things that are much more in line with some other research patterns that we had in the past. Now, let me say that in terms of research agenda for the program, we have both modeling the physics of the problem, but one of the important reasons why we picked this problem is because from the computational perspective, the methods that you use to characterize the turbulent flow, the particles, and the radiation are very, very diverse. So they force you to really identify different algorithms and different computational techniques for each one of these components. And these, as you will see in a moment, will become critical when you try to do exascale computing or high-performance computing. The uncertainty is also part of it, and is related to the fact that, for example, particles, although nominally homogeneous, they don't have the same characteristics. So the diameter and other things are characterized by distribution rather than unique values. Now, I don't want to tell you much more of that. I just want to switch to the exascale part and very briefly mention the fact that, as you know, and you will see this plot probably many times during the talks this morning, the speed of the fastest supercomputer in the world has been increasing in the last 30 years in a logarithmic plot very, very consistently. And according to this, in 2018, we should actually reach exascale computing or exaflop capability with as long as we have the money to construct the system itself. So this is the picture. Now, I'm not a computer scientist, so in terms of telling you about our effort and the road to exascale, I decided to use a sort of an analogy, and this is my analogy. So the idea is that today we're really very comfortable on teraflop systems, and we do have capabilities and availability of petaflop system, maybe not for everybody, but still it's something we can access today. But this is where we need to be if we want to be able to use or to work on exaflop systems. Now, the reason I'm plotting this is because what I'm going to focus on and what our program is focusing on is not the hardware, but it's actually the interaction between the users, in this case, and the hardware itself. And this is how it looks like. So the interaction is really, fairly trivial and straightforward today. It gets a little more complicated when you think about a petaflop system. You have a lot of things you worry about, but obviously in an exascale system, things are way, way more complicated. And extracting performance out of this system means that you have to master this interface. And this is sort of the challenge that we are taking on. In addition to this, I don't expect you to read this, but this is the 5 top supercomputers in the world according to the top 500 list. The architecture is extremely, extremely diverse. So this means that this interface is even more critical because every time the hardware will look different. And so obviously from a computational scientist perspective, you don't want to have to know too much of these machines to handle them. And so this is the typical picture we have of our graduate students sort of having to deal with this problem. And performance is a key issue, but it's not the only issue. So again, I want to give you sort of a very, very brief timeline and telling you, now I went much earlier than the initial start of the project. So this is in the early days, before 1980s, this was sort of the picture that we had, and this was one of the first supercomputers becoming active here in the Bay Area. It was the HPCAC 4 at NASA, and interestingly enough, I don't know if you want to read this, but this is one of the software, or the main software designer for this system, that sort of acknowledged that our way to interact with the machine perhaps was not effective or not very efficient. Well, it turns out scientists at Ames, and I'm referring here to Bob Rogallo, who is one of the leaders at NASA Ames that really took this on, were able to actually write computer codes. In this case, CFD or Vectoral was a specific computer code that was designed to handle that machine very effectively. This was one of the first parallel machines, but it had very little memory, for example. So there was a very difficult to handle a complex calculation like a turbulent flow with such a small memory footprint. So this is to say that it was a challenge, but also an opportunity to really bring communities like the scientists and then the computer scientists together. Now, after that, the picture has been a little bit different. We have we have had a debate between vector system and then massively parallel system. This was exactly the days where we have been sort of focusing on the ASCII calculations. And in this case, obviously, we ended up in this program with sort of relying on clusters and MPI as our programming system, very, very consistently. It turns out that though in the last part of the program, here at Stanford, we invested quite a bit of that effort, of the PSAP effort, developing and thinking about a new system, a new computer system, a new supercomputer system, in particular called Merrimack, the streaming supercomputer. The interesting thing about this program, this was led by Bill Daly and Pat Anran here at Stanford in the computer science. It also had a software component. The software component was called Brook, as a relation to Stream, I guess. And Brook was really, you can trace an almost direct line between Brook and CUDA, which is the current software system or software development for GPUs. This was a very, very influential program. In fact, Bill Daly will talk afterwards, and obviously is a senior vice president at NVIDIA, not surprisingly actually. But the other thing I want to point out is that even at that time, there was a very strong, again, collaboration between the computer scientists and people working on fluid dynamics on the same type of computers. After that, this was, as I said, really a spin-off activity trying to go in a different direction. But then in PSAP, we actually embraced the computer science part. And there the development was on domain-specific languages and specifically Lisp. Lisp is an interesting concept because it brings the application directly into the programming system. So this is a language that was really developed for PDEs, for mesh-based PDE solvers. And so we sort of went, if you will, full circle from a machine-specific programming language to a domain-specific or to a physics, to an application-specific programming language in the course of 40 years with very interesting connection, again, between computer scientists and, in particular, fluid mechanics in this case. So this is where we start with PSAP 2. Lisp is, in many ways, as limiting or as sort of a starting point as CFD, as this ILIAC program was really not very flexible, was an idea or an initial step rather than a fully mature product. But as I said, out of this, there was a lot of development in vector machines. We hope that Lisp will be able to spin off similar ideas. And in fact, in PSAP 2, that, as I said, is just starting, there are three components of our exascale effort. The first is the 2.0 version of Lisp, which is not just PDE, but adds additional components, physics components, but also interoperability to be able to access additional libraries and so on. There is a component that is specifically designed to work on managed data locality, which is a key aspect that you will see more discussed in the morning, but also architecture-specific parallelism. Different machines will require a different type of parallelism, and we are not going to expect the programmer to actually be able to make those decisions. So they will be sort of handled directly by the runtime and the system that is behind. And then there is also a component very important that handles fault detection and resiliency, that at those scales become critical issues. So I'm not going to go spend more time. I actually am almost exactly on time. So I'm going to finish here. Mine was really, as I said, an introduction to this workshop. I hope you will enjoy the talks that come after me. We have, as I mentioned, an extremely interesting set of talks, and I want to thank again everybody for being here. I want to thank all the speakers to accept my invitation, that have accepted my invitation to the workshop. And in thanking you, I'll introduce the first speaker, Jack Shen, in a second. Thank you.